Now, let us find out the Cauchy's theorem, which tells us the stress component. Just 1 second. The stress components on an ideal plane. We know in this subject of solid mechanics, we are interested to know the stresses or component stresses on a particular point in space, not on the we are not no more interested in the average stresses over any particular plane. So in order to do so, we have taken certain discussion about how we are supposed to be represent the stresses at a point and how we are using the free body diagram concept to calculate the stresses. Now, let us find the stress components of a particular point. We know the stress, if we know the stress, what is the value of the stress component acting on two mutual perpendicular planes passing through a particular points, then we can calculate the stress component on any plane passing through that point. So what we are supposed to know first, there is a point which we are supposed to know. We are dealing with the three mutually perpendicular planes, x and y and z, in three mutually perpendicular direction, just shown in here, x, y and z, x for rightwards positive, y upward positive, z leftward positive, etc. And it is negative in the opposite direction, which is also sometimes necessary to know. Sorry. Now, the stress components, if we know the stress components of these particular points in along these three direction x, y, and z, and we can calculate the stress component on any other plane, which is passing only one condition is there, it should be passed through the point P. So P is the basis. We know the stress components which are passing through P, and we are now confident that if we got any plane who is defined by a normal n or any normal which is defined by a plane passing through the point P, then we can get the stresses acting over these planes also. That too are passing through the point P. This is the basis of our assumption, basic assumption over which we are doing this particular equations known as Cauchy's equations. Now, let the three mutually perpendicular planes which is shown is here, and let an arbitrary plane be identified in outer direction. Let the arbitrary plane be identified by the outer direction, outward drawn normal n. So we want to know the stress over an arbitrary plane, which is not known to us, not available at this moment to us, but it is defined by its outer drawn normals n. Means I have told you a number of times, a plane in space is supposed to be defined by the normal acting over it, and a normal which is defined in the space also must be normal on at least one of the plane itself. So both can define each other. And what we need to know is a point over which an infinite number of planes can pass through, and as infinite number of planes can pass through, there is infinite number of normals can act over these planes and as well as acts over this point itself. So in order to, we are picking up only one of them, and which is defined by a normal n, which is acting over normal to it and drawn outwards. Now, this normal is supposed to have a direction cosine. This normal n, which is shown here over this particular plane, which is I am soon coming to the details of it. If this normal n, if normal is n, should supposed to have direction cosine, means if it is resolved into three mutually perpendicular plane in x direction, it should be resolved by multiplying the normal, either length or the force acting over it with the direction cosine, means the cosine of the angle which is met with the respective x, y, and z axis. So direction cosine is nothing but the cos of the angle made by a particular normal through which a force may be acting on along act along to it, a force may be acting on parallel to it, but this normal supposed to be the cosine of this normal, which normal may be its length, normal may be a force. The cosine of this normal is supposed to be called as direction cosines, which is defined as existence along x-axis and y-axis and z-axis, which is defined as nx for x-axis and ny for y-axis and nz for x-axis. That is the cosine of the normal. So first we got the normal to define the plane. Next we are defining the normal by its direction cosine by resolving it into three mutually perpendicular direction by multiplying multiplying its value by means of the cos of the angle it intended to x-axis or x-axis or z-axis. It the cos can be this angle may be same, angle may be different as per the position of the n itself. Just 1 second. Stop share. Now that is not self-fancy. Now just I have told you the direction cosines are nx, ny, and nz along x and y and z direction itself. Now, consider a small tetrahedron. And you know what is tetrahedron? It is a triangular pyramid. Pyramid, what do you mean by pyramid? Everybody knows what is pyramid, but actually, what do you mean by pyramid? You should understand properly before going through this type of equations. Pyramid should have a base, maybe round, square, triangle, rectangle, or whatever it may be, and it should go and all these sides acting from its base will reach each other at a single point, which is called the apex of the pyramid itself. So it looks like a uh, sharp is a conical like a cone, or pyramid is like a is one type of cone itself. Here we are using the help of a tetrahedron. It is a triangular pyramid, means its bases are triangle. All the sides are triangle. It has four sides, like we have shown here in the earlier. Just I'm showing you again. Here we have this pyramid. This is a tetrahedron, which is a triangular pyramid, which we have, say, one of the triangular base. There is a triangular side, this is a triangular side, and this is also a triangular side itself. So 1, 2, 3, 4. Four triangular sides are there in a pyramid itself. Over which what we are doing is we are placing this corner of we have 1, 2, 3, 4 corners of the pyramids, four sides, four corners, and we are placing the pyramid in such a way we are placing the corner one corner at the point at our desired point P itself, and we are showing all our known components of stresses over which is available along x-axis, y-axis, z-axis, and over the different planes of the pyramid, this plane, and this plane itself. Sigma x, sigma y, tau x, tau z, all these things, tau x, y, all these things are shown here. Now, what we are going to do is, what we are going to do, now let h be a perpendicular distance from point P to the inclined face which is facing the edge. Not any, only one of the plane is not along any of the x plane or y plane or z plane, which is just facing the P plane P, and we are understanding that R H it is not R but H is the perpendicular distance from the point P to the inclined plane, and This inclined plane is supposed to have its normal parallel to n itself. I am not saying that normal is exactly along the plane, but it's supposed to be parallel to the plane itself because its orientation can vary. So we cannot say that normal which is coming out of the P and coming out and which is passing through exactly at the normal through the normal, but I am saying that this normal of this plane is parallel to the normal n itself. And H just have told you the perpendicular distance of P from P the inclined place. Now let us isolate this tetrahedron or triangular pyramid from the body of this body from which it is situated, a part of the body, and we got a free body diagram is drawn. Then this free body diagram, our conception of free body diagram, it should be perfectly equilibrium under the action of surface and body forces. We told you what is body forces, what is the surface forces. Surface forces are different external forces like which may be concentrated in nature, may be distributed in nature, may be reactionary force due to the support of the said prismatic bar. And the body force may be the force of the inertia, force of the magnetic force, and force for the just 1 second. Uh, Inertia force, magnetic force, and yes, one of the most important force, inertia force, gravitational force may not be there, but inertia force or magnetic force may not be there, but gravitational force must be there. Three types of forces like gravitational, inertia, and forces are supposed to be the surface force. So this particular pyramid is under equilibrium under the action of all external forces, which is shown there, plus also under the action of the surface forces acting over it. Now, what is our assumption here? The size of the tetragonal considers to be very small, infinitesimally small, and in the limit as we are going to make h tends to 0, but it is approaching p, almost reach the p, but not exactly reach the p. As our mathematical decision is like this, it tends to be, doesn't means tends to a certain distance, doesn't mean equal to the distance, but it is the closest to the distance, and this difference between the distance is infinitesimally small but not equal. But we see, say h tends to 0, we speak in terms of the average stress over the face itself. We have four faces. One is approaching, one is in front of us, and other three are along the three different planes. Let us assume the external force, surface force Tn, with the resultant stress vectors on the face ABC, means on this front face. This can be resolved into three forces. So we are understanding due to this uh, free body diagram, we are getting the average resultant stress vectors, which is the effect of other adjoining free bodies, comes as the resultant T as Tn. It is on the acting on the face itself, may not be normal, and this can be resolved into the component Tx to the power n, x, y, n, and z. Means this force is acting along the normal, and it is resolved into Tx, Ty, and Tz along x-axis, x plane or x-axis, y-axis, and z-axis itself, and or parallel to the three axes, not exactly along it, but parallel to the three axes. On the three faces, the rectangular stress components we have already shown, which is acting there, is sigma x, tau xy, and tau xz on x plane, sigma y, tau yz, tau yx, one y plane, sigma z, tau zx, and tau xz on z plane. Now, we are understanding that A is the area of the inclined face. Just 1 second. Is the area of the inclined face ABC. Let A be the area of the inclined plane. Then area BPC, projection of area ABC on the YZ plane, is given by area multiplied by the direction cosine. Area of CPA, projection of the area ABC, means found triangular faces on the XZ plane, that is ANY. And area IPV, projection of the area ABC on the XY plane ANZ. Just I am showing it again in the earlier picture. Actually, this is a mm, this is our plane A, B, and C. On this plane, we have other three planes. One is along YZ axis, one is along XY axis, one is along Z axis. And we are assuming we have already got the direction cosine of the normal of this plane along as along x and y and z axis is nx, ny, and nz. And we are assuming that area of this triangle is equal to A, capital A. So we can have assume, we can understand that area of the triangle, say that is A, uh, ABP, which is along XY plane. ABP, area of the triangle will be area multiplied by the direction cosine nx, which is we have formulated here. Area uh, area APZ means this area is equal to the direction cosine of the area acting along Z itself and Z, and area BZ BCJP is the direction cosine of the area A itself. That is equal to the A multiplied by the NY itself. This is NX is here. So we are getting this angle multiplied by NX. NY is here. We are getting this angle multiplied by the getting this figure multiplied by this thing, and NZ is here. But we are multiplying this area with the NZ here. But this triangle, of course, have one NX here and NZ here, NY here, NX here, like this. But we are multiplying either NX, either NY, and either NZ to define the plane in terms of A itself. So BPC, it's BPC is the ANX, BPC is the ANX, and CPA is the CPA is the projection of the around XZ plane, XYZ plane. So projection of the area on the YZ plane is multiplied by NX. Projection of area on XZ plane multiplied by Y and Y, and projection of area on the YZ plane is multiplied by Z and Z. Explain means nx, it is being multiplied by that those direction cosine which is normal to that particular plane itself. Nx, the direction cosine of n is perpendicular, nz is perpendicular to xy plane, ny is perpendicular to xz plane, and nx is perpendicular to yx plane, where n is the normal and its direction cosines are nx, ny, and z. Now let the free body diagrams, the body forces, the forces components in xy direction may be gamma x, gamma y, gamma z. Body force, like say your magnetic, inertia, gravitational force, etc. We have the force component along gamma x, y, and z respectively per unit volume. The volume of the tetragonal we are calculating like this. The volume of the tetragonal equal to 1/3 A into H. A is the area and H is the perpendicular distance from P to the inclined area. This is the equation of the volume of any cone, any prism like this. And now the equilibrium, for the equilibrium of the tetragonal itself, the sum of the forces in x, y, and z direction must individually vanish itself. Otherwise, it cannot be in equilibrium itself. It cannot be in equilibrium. So sum of the forces x, y, z direction must be equally vanished. So what are the sum of the forces x, y? We have already have tx drawn, tx multiplied by a itself. It is that form t into a component of the force t along x direction, and which is being multiplied by the area over which is acting is a, and sigma s is a into nx. So you have got that sigma x and sigma tau xy a into ny. Similarly, sigma z is a into nz plus 1/3 ah gamma x equal to 0. Now we cancel the a, it is common to all of them. So tx, the force component of force which is acting along the n along x-axis is equal to sigma x nx, tau xy ny, tau xy nz, and 1/3 h gamma x, which is gamma x is the component of surface forces along x-axis. Similarly, in the same fashion, we are having the equilibrium in y and z direction, that is ty is equal to n tau xy nx tau sigma y or tau xx equal to ny, tau zx equal to nz minus 1/3 h gamma y, or as well as t to the tn z is equal to tau zx nx, tau yy ny, phi z ny, and sigma z nz minus 1/3 h and gamma z. Just we are solving the problems along x, y, and z axis. Solving all the meters, all the external forces, all the forces acting over this tetrahedron, which is used as a free body diagram. And as per the free body diagram, all the forces should be, it should be perfectly in equilibrium. So we are applying all the forces in different sections of it. Next course. Now, in the limit, as we are saying that this triangle having the area A is approaching to P and closest to P, but not equal to the, its h tends to show the distance of this angle P, of this area A from the point P is tends to 0. The oblique plane ABC will pass through the point P. We are assuming this oblique plane ABC is passed through the point. The average stress components acting on the force will tend to their respective values at the point. All the average stress components acting over the faces will now tend toward respective values OA at point P acting on all the forces will tend to their respective values as at point P. Let us go for the next page, that is 8. They are corresponding plane, that's why consequently this equation reduces to, we have all the gamma x, y, z terms are vanished as it is approaching to 0. So txn is nx sigma x, ny sigma xy, nz sigma xz, and nx tau xy, ny sigma y, nz tau yz, and tz is equal to nx tau xy plus ny tau yz plus nz tz. So as per our definitions, we know the values of tx, sigma x, sigma yx, tau xy, all these 9 parameters we are supposed to know to us in order to know the fraction, know the component of the stress acting over the of any plane passing through it. So this is the equation. This is three equation is defined as Cauchy's stress formulas. Cauchy's stress formulas is one of the most important equation he has derived. This shows that this line rectangular force stress components, there are nine, 1, 3, 3, 4, 5, 6, 7, 8, 9, are at P will able to define the stress components of any arbitrary plane. Means this is supposed to be known to us, and to know the value of stress in any arbitrary places defined by x, y, z, its component as well as the resultant can be safely calculated if we with this knowledge. Now, among these nine forces, six forces are independent and others are independent to each other, and others like this: sigma tau xy is equal to tau xyx, tau z is equal to tau xy, and tau zx is equal to tau zx is equal to tau xz. This is the they are not, this is called equality of cross shear. As per our um, shearing stress equation of shearing stress, only every shear is to be accompanied by shear stress accompanied equal and opposite stress on the adjacent stress. This equation also values that the xy is equal to the its parallel but working in the opposite direction yxy, and yz is equal to tau yzx, which is of same value because to make the equilibrium yz and acting in a different direction, and tau zx is equal to tau xz for the same reason. This is the equality of cross shear, which you know from equilibrium of stresses for cost stress, equilibrium of stresses for shear stress. Now, these results above equation can be reduced. Ti means I represents the your planes x, y, z, nx, tix, ny, tau iy, nz, tau iz, which is equal to, again we can shortly write down as sigma j, nz, j stands for x, y, z, and tau iz, j again z formed from z, y, and x. So this equation sigma tau I is given as sigma j nj tau j I, where I and j can stand for either x or y or z, and tau x, sigma x we can safely write down as tau xx, sigma y is equal to tau yy, and tau z is equal to tau iz. Now, P is the resultant force acting on the plane AB. Now, T is the result, T to the power T vector n is the resultant stress acting on the plane ABC itself. So, whose component are Tx, Ty, and Tz. So, we can safely say that T square is equal to Tx square plus Ty square plus Tz square. So, if you know Tx, y, z, Tx, Ty, Tz, we can have the resultant stress on the plane AB, which is defined by the normal n itself. Now, if sigma n and tau n are the normal shear stress component acting over the plane AB, we can say tau n of ABC acting over the plane ABC, then we can say T to the power n whole square equal to sigma n square plus tau n square. Since the normal stress is equal to the projection of T to the power n along the normal stress is equal to the projection of T to the power n along the normal. It is also equal to the sum of the projections of the components Txn, Tyn, and Tzn along n respectively. So what is saying here? Normal stress acting normal to ABC is equal to the normal projection of Tn along the normal. This is the normal stress. The projection T is equal to the projection of Tn along the normal. This is the normal stress. So it is also equal to the sum of the projection of the components Tx, Ty, Tz. So sigma x is, again we can write down like this: sigma x is equal to Tn nx Tx to the power n, ny Ty to the power n, nz Ta to the power n. As we have already made Tz, Ty, Tx is accordingly. So sigma n, which is acting normal, and our normal n is acting parallel to the normal itself. So this can be resolved into sigma n normal to it and tau n normal along with sigma n along the space and tau n along the normal itself. Now, thus the sigma n we are putting, again we are using the cosine values and multiplying these reaction cosines and multiplying the value of Tx, which is acting along x-axis, and y, the projection of the components will actually, this is the projection of the component of T, and if we multiply the reaction cosine, you will get the projection of the component of sigma. So sigma nx to the power n is equal to n plus ny Tz to the power n plus nz Tz to the power n itself. So we have got Tx, Ty. We can I already have Tx to the Tx n, Ty n, Tz n. So we put the value of Tx, Ty, Tz from here. We'll have equation. We'll have this equation sigma n equal to nx square sigma x, ny square sigma x, nz square sigma z, etc. And 2 to nx, ny, nz, 2 to nx, ny, nz are like this. So we can use this first equation to calculate the value. We can use the first equation to calculate the value of Tz itself and the value of tau n itself from here, because we know this Tn square as well as we know that sigma square, sigma n square. So let us go through certain practical problem which will make it clear to you. Achha. A rectangular steel bar having a cross-sectional area 2 centimeter to 3 centimeter. It is subject to tensile stress equal to 6,000 Newton or 6 kilonewton or 6112.2 kg force. And if the axis is shown as here, is one axis here, another is here, axes are like this 1, 2, 3, then find out the normal shear stresses on a plane whose normal has the following direction cosines. So find out the normal and shear stress on a plane. We have the rectangular bar, we have the externally applied force on a particular plane itself. We have the size of the plane itself, so that we can get the value of stress itself. Now, the axes are shown here, and the normal and shear stress on a plane whose normal has the direction cosine, following direction cosine, whose normal has the following value of cos is nx and y is square root by 2 and nz is equal to 0. Then what will be the normal and shear stress on this plane? The plane is given by its direction cosine, but we have to find out the normal forces, shear forces. And the force T is also given as 6,000 Newton for as per the given norms itself. Now, area of the force area of this section is very clear, 2 into 3, 2 centimeter into 3 centimeter gives you 6 centimeter square. The average stress on this section will be the force divided by the stress, 6,000 by 6 is 1,000 Newton per meter square. And this is the normal stress sigma y, sigma x, and sigma z is 0. So Tx to the power n, we can use this Cauchy's theorem. The normal stress we y and x, this is the normal stress y we are supposed to know, and this is because we are having the force acting along y-axis, so sigma y is available, and no force is there for x-axis and z-axis, so there is which is equal to 0 itself. So Tn square, we are using the Cauchy's formula, nx, this is given, nx sigma x, sigma tau xy, everything is, we put the values in, and T is equal to Tx, and T is sigma n square plus Tn square. These are the formulas we should supposed to do. And sigma n is equal to sigma x, Tn to the power n, sigma ny, T to the y to the power n, and z to the power n. Okay. Now, character couple cosines are given as nx and y is equal to square root of 2, and nz is given as 0. So we can, as sigma x, sigma y is 0, and sigma y is sigma x and sigma z is equal to 0, as there is no force in x and y direction, and sigma y we have a force n 1000 meter per square meter per centimeter. Is tau z, tau x, anything, any force along z direction, z, x, y directions are all 0. So T to the power x is equal to 0 to the power y is given as here ny and sigma y put 1 by square root of 2 into 1000 from equation 2, and sigma c, sigma z is equal to also equal to 0. Thus sigma n is how square root of this one getting from this equation here, and ny here, which is 1 by root 2 into this value of ty, which is equal to 1 by root 2000, which is given as 500 Newton per meter square. And what is t? T to the power n is the square of this value of ny, as tx and ty is all 0. So this is equal to 1000, 10,000 to the power 10,000 square divided by 2 itself, or 5 lakh is equal to 5 lakh itself. Thus, sigma tau n is equal to tau t to the power square minus sigma n, or is equal to 50,000. I'm sorry, 5 lakh minus 2,50,000 is equal to 2,50,000 itself. So tau n divided by, so tau n, if we make the square root, the tau n is equal to 500 Newton per centimeter square. More or less our time is limited, nearly off. I am stopping the session.